Hello and welcome back. Just a quick note before we jump into the video. After I finished recording, I noticed that it might be a bit hard to follow the calculations all at once, so I decided to start a little website to go along with this and potentially future projects. There you can find all the formulas, additional explanations and background information about the project. If you want to take a look, you can find the link in the description below as well as on the screen right now. And now, enjoy the video. So while I have been calculating the tube amplifier, I noticed something that annoyed me quite a bit. You know, as I said, I built this amplifier like 15 years ago, whatever, and I had no real idea how to do it properly back then. So I just thought, well, let's take a look why that was the case. Why did I not really calculate everything from the beginning and do the circuit right? And I think I remember again why I did just eyeball most of the things. You know, there is a wide variety of technical literature about tubes. For example, this, or this, or that, or this, that, maybe even that, or these, that, or one of these 5 other books that I have. All of them are good in itself, but I noticed none of these books really show you how to calculate an amplifier from the beginning to the end. Every little step to just start out as a beginner. If you ask in many discussion boards, online forums, whatever, there was quite a culture of just saying, well, yeah, just get these books, read them, understand them, and you are golden. Well, I read all of them. Yes, if you read these, you understand everything. But you have to keep in mind, this is literature from many decades ago. It is written in a way that is not really inviting nowadays. It is really, really hard to read. And I would assume many people probably died trying to read that. So I do not recommend going that route. For all means and purpose, if you want to, feel free. Get these expensive books. But yeah, maybe you want to just tinker around a bit with stuff that you maybe salvaged from an old radio or whatever, and just get going and see if this hobby is something for you. And that is the reason why I said to myself, let's try and make a little short-ish beginner series going from step to step, how to build your first tube amplifier from scratch with let's try that word again, with components that you have lying around. Yeah. So let's get rid of this. Oh, and by the way, to everyone probably hating on me, for example, because I showed that book, I know Jochen, so Johan Gittel, I know him in person. He's a nice guy, but even his book is not giving the introductory notes that I would have loved. So, yeah. Nothing personal about the authors of these books. I bought them, I read them, I like them, but something is missing. So, how do you get started building a tube amplifier? Well, if you have parts already lying around, the first thing you need to know is, what are my output transformers? you have to measure them and see what impedance ratio they have. What is the primary impedance? Ideally, what is the secondary? But usually you just can guess if you do not have the original speaker it came with. And even if you have, most of them have no markings about the impedance. So yeah, good luck finding that out. So we have to measure them. There are several ways to do this. A very simple one is using just a mains powered transformer backfeeding into these and measuring voltages, which is kind of the way that we are going to go. But this is where the little amplifier that we built in the last video comes to play. I just cut off the PCB and shoved it all in this neat little box that I had lying around. So yeah, we will be using this one and do it a slightly nicer way. So an audio transformer basically translates the speaker impedance to the tube's impedance. As we know, hopefully, tubes have a relatively high impedance in the kilo ohms range, and speakers have a impedance in the lower ohms range, around 4 to 8 ohms usually. As you see, we have a pretty big mismatch there, so the transformer is here to help us transforming the impedance of the speaker to the tube. So let's take a look. The interesting question here, of course, is what actually is impedance? Well, impedance is, you all know Ohm's law. It is basically the impedance for AC voltage or current. So the same calculation as you know from Ohm's law, R equals U or V over I, is the same for impedance, just that you replace the R with a Z. So yeah, the impedance is also the AC voltage over the AC current. Good thing for us here is we know the secondary impedance, but we do not know the primary impedance, which is necessary for calculating our tube amplifier. So, how do we find out more about the impedance? To decipher it, we basically have to know what is the winding ratio or the turn ratio of a given transformer. Also, I just noticed I have to work on the white balance. My fingers are usually not pink. Whatever. Let's not get distracted. The turn ratio unfortunately has several names. Here in Germany we just name it with a small Ü. This is that letter. You have probably also seen N and K. For ease of writing of foreigners, I just use N in this example here. So what is the turns ratio? The turns ratio is basically how many windings of wire is wound on one part of the bobbin of the transformer divided by the part of the secondary winding, which is also wound on the same bobbin of the same transformer. So it's basically the ratio between two different numbers of windings on the same transformer bobbin. This is also the same ratio as the voltages from primary to secondary, because this is only dependent on the number of turns ratio. And also we can see for current it is the inverse, because, well, physics. We can't get more energy out than we put in. So if we transform the voltage up, the current has to go down and vice versa. Knowing what we just learned, we can do some basic calculations to determine basically every of these four values here by just knowing the turns ratio and one of the other values. So as you can see, for example, we can calculate the V2 voltage by knowing V1 and the turns ratio, or we could, for example, want to know the secondary current, so I2, which is the primary current times the turns ratio. Pretty simple so far, isn't it? So let's get back to the impedance. We want to know what our primary side impedance is. So we know from before that V1 over I1 equals the primary impedance. Now we can replace V1 and I1 by the values known here. So that we have for the primary impedance is V2 times the turns ratio over I2 over the turns ratio. And we can calculate and shorten that to have the secondary impedance times the turns ratio squared equals the primary impedance, which we can see here. Also, we can inverse that to, if we want to know the secondary impedance, we just have to divide the primary impedance by the squared turns ratio. And that is basically everything you know. These little formulas is all you need to know. So if, for example, let's make a quick example here. If you say we have for example, an output transformer that has a secondary impedance of, for the sake of easy calculations, let's say we have 10 ohms. And we know that our turns ratio is, for example, tenfold. So we have N is 10 as well. We know that our primary impedance must be 10 ohms times 10 squared. So that is 10 ohms times 100. So we have 1 kilo ohms for this transformer. Simple, isn't it? So I have prepared the measurement setup. We have two multimeters. You can also use your scope with readout or even without. It's totally fine. You also don't have to use such fancy ones like I have. You can absolutely do it with one of these. I just chose these because they are better in terms of visibility in the camera. We have the little audio amplifier, which is connected by these BNC, well, banana jacks to BNC adapter to my signal generator. And here I have my power supply connected. It is just outputting 22 volts, which we can feed into the amplifier. And the signal generator is outputting right now 1 kilohertz sine wave. So this is basically the measurement setup. Just feeding a known voltage into the output transformer and measuring what gets transformed to the primary side so that we can do the calculation that we did before. You might ask, well, why do you all these complicated things with this extra audio amplifier and using a signal generator outputting 1 kilohertz when you just could use like a 6 volt transformer and connect it into the output transformer's output, secondary, whatever you want to call it. There is a reason to that. Output transformers have basically a characteristic. Let's see if I can quickly draw that. So if we want to plot like the transformed voltage over a frequency, we have roughly like these characteristics. We have a dip at the beginning and a dip at the end. In the middle it might be pretty linear, we don't know that, but it could be. However, we want to try to measure more in the middle area where it is probably flatter than at the complete beginning and the complete end. So we do not want to measure with like 10 megahertz, it will probably not do much. We also want to avoid measuring at 50 hertz, which is pretty damn near here this beginning part. So we want to push it a bit further in. We could also use like 10 kilohertz, which is usually completely fine, but 1 kilohertz is a pretty standard value as well. So let's go back to the measurement. I will quickly connect the power to the amplifier, and then I will use the hold function on the multimeters to basically freeze the voltage that we can see here. So let's do that. Put that out, and there we have our voltages. Let's put that into here. So our V1 equals 37.742 volts, and our V2 is 0.8660 volts. And knowing these, we can remember our formula that the turns ratio is V1 over V2. So let's put that in the calculator. Turns ratio N is 43.58. So to prove the point of using this slightly more elaborate setup using the audio amplifier instead of just using a 50 Hz transformer, I redid the whole thing with just 50 Hz frequency, and well, I had to turn it a bit down, the gain of the amplifier, because, well, the whole output transformer decided to be a speaker at the levels we had before. So I had to turn that down a bit, but it doesn't matter, the relation stays the same. So if we calculate that now, I try to make it visible again without glaring. So we have 10.408 divided by 0.2489. We get 41.81 at the 50 Hz. So as you can see, there is a noticeable difference. You might say, well, this is not much, but remember, the turns ratio gets squared, so also the error gets squared. Yeah, so we try to be as accurate as possible. But if you do not have a signal generator and do not want to build like this little amplifier, you can of course just do it with a 50 Hz transformer, but it won't be quite as accurate as you could be. So let's get back to the calculations and finally determine what our primary impedance for this transformer is. So I did two more measurements using 10 kHz and 20 kHz, and you can see that the curve is actually getting a bit flatter. I also did a measurement with, just for fun, with 40 kHz, and it basically was off the scale. So yeah, no idea just out of my head what happened there, but probably there were some resonance effects, I assume, because that was very, yeah, it was going like giving out 200 and whatnot volts. Yeah, that was a bit extreme. So don't go overboard, don't go too hard. So whatever, we did the measurements, and as you can see, these three in the audible range are quite near, and going down to the bassy range we are flattening quite substantially, which also returns a bigger measurement error. So for calculating the primary impedance, I just assumed that the secondary impedance would be around 6 ohms, which is not too uncommon. So, you know, your typical speaker is around 4 ohms or 8 ohms, and we will come back to that in a second, which effect this has on the whole tube amplifier. But let's just do a middle way kind of thing and just assume 6 ohms. So we have the formula, Z1 is Z2 times the turns ratio squared, which is of course 6 ohms times the turns ratio squared. And here I calculated all these values for the 4 frequencies we used. So for 50 Hz we get a primary impedance of around 10.5 kilo ohms, and the other 3 are around 11.5 to 12 kilo ohms. So I think we can say that this transformer is, if we use it for a 6 ohm speaker, it would be good to calculate with around 11.5 kilo ohms for the primary impedance. Now, what would happen if you do not connect a 6 ohm speaker but instead a 4 ohm or an 8 ohm speaker? Well, this changes things quite dramatically. So let's just take a quick look at this and ignore that I scribbled here and miswrote. So for 4 ohms, the primary impedance would only be 7.5 kilo ohms, therefore substantially, giving way more current or taking way more current from the tube than it would be for the 6 ohms. On the contrast, if we go for 8 ohms, we will be way under the current, and therefore our working point would be quite off as well. So this shows how important it is to know which speaker you want to connect to the output transformer. Ideally, you would choose an output transformer that fits your speaker and choose a tube that fits the corresponding impedance, or better, calculate the amplifier in a way that it does. But you can't always guarantee that. So sometimes you have to take a look and see what would be the best compromise for all use cases. So I just chose to calculate with 6 ohms. This gives me a rough middle estimate. So yeah, we can work with that. And this is basically all you need to decipher a unknown audio output transformer. It's not that hard, is it? Just a quick last-minute addition before we end this video. If you have a known transformer, like you bought a transformer which is like an 8 kilo ohms transformer which is used for 8 ohm speakers, but you happen to have 4 ohm speakers and want to know what impedance you can expect and what you have to calculate for, well, there's also a pretty simple formula. You just calculate the turns ratio again. This time it is the square root of Z1 over Z2, which in terms of this 8,000 ohms to 8 ohms ratio, which will returns in a 31.622 turns ratio. And if we put that into our formula for the impedance calculation, we have again n squared times Z2. So we have 31.622 times 4 ohm. Oh, I forgot the squared. This is of course 31.622 squared times 4 ohm, which of course results 4 kilo ohms. Hooray! Math. Simple.